All right, today we are tackling a real powerhouse of probability, the law of total probability. Honestly, the best way to think about it is as your secret weapon, your ultimate divide and conquer tool for taking a problem that seems impossible and just breaking it down into simple, solvable pieces. Let's get right into it. So picture this. Let's say a system can fail in a few different ways, right? Maybe a software bug, a hardware failure, or I don't know, a power outage. Each one has its own likelihood. So how do you figure out the total chance of failure? You can't just add them up. It doesn't quite work like that. This is exactly the kind of puzzle we're going to solve today. So here's our game plan. We'll start with a tool you already know, then get into this new divide and conquer strategy. We'll unpack the master formula, use it in a real-world example with some factories, figure out when to use this rule versus others, and finally talk about why it's so incredibly important. Okay, first up, one path, one answer. Before we jump into the new stuff, we've got to do a quick refresher on a concept that's basically the building block for everything else. You probably remember the good old multiplication rule. It is perfect for finding the chance of one specific sequence of events. What's the probability that event A happens and then event B happens, assuming A already happened? This rule nails that answer for just one specific path. And that right there is the key difference. The multiplication rule is for a single road. It answers a very specific question, like what's the chance a part came from supplier X and it was defective? But the total probability rule, the one we're learning now, answers a much bigger question. What's the chance a part is defective, period? It doesn't care where it came from. It adds up all the possible roads that lead to that defective part. Which brings us to the core of it all, the divide and conquer strategy. This is our whole approach for taking a big, complicated problem and slicing it into clean, simple pieces we can actually work with.
And the magic word here is partition. Just imagine that the entire universe of possibilities, what we call the sample space, is a giant pie. When you partition it, you're just slicing that pie into pieces. The only rules are the slices can't overlap, and every single possible outcome has to land in one and only one of those slices.
And this is what it looks like. Our whole world, our sample space, is split into three totally separate scenarios, A1, A2, and A3. No overlaps, and together they make up the whole thing. That's a perfect partition. Okay, now let's say we're looking for something specific, an event we'll call B. Let's think of B as the cherries in our pie. The cherries could be scattered across all the different slices. So, to find the total number of cherries, you don't look at the whole pie at once. Instead, you figure out how many cherries are in slice 1, then how many are in slice 2, then slice 3, and then you just add it all up. It's really that straightforward.
Okay, time to look at the blueprint. Let's see how this whole pie analogy gets turned into the actual math, the core formula we're here to learn.
So the first piece of our formula is P of A. This is just the probability of any given scenario happening. In our pie analogy, this is literally the size of the slice. Is it a huge slice of the pie or just a tiny sliver? This tells you how likely that scenario is to begin with. And the second piece is this conditional probability, P of B given A. This asks a different question. If we're already inside one particular slice, what's the chance of seeing our event B? So back to the pie, this is just the density of cherries inside that one slice. Maybe one slice is packed with cherries and another barely has any. And now we put them together. Using that multiplication rule from before, we can find the total amount of cherries in just one slice. We just multiply the size of the slice by the density of cherries inside it. That calculation gives us the probability for just one single path to our outcome. And here it is. This is the big one, where everything clicks into place. Let's walk through this, because this is the heart of it. That top line is the multiplication rule for one path, just like we talked about. Now look at the second line. This is the big idea. It says the total probability of our event, P of B, is just the sum of the probabilities from each of those individual paths. That big E-looking symbol, that's sigma. It's just a mathematical instruction that means add them all up. So we calculate the probability for each path, and then we sum them together. And that third line shows you exactly how it looks when you write it all out. You calculate the value for path 1, you add it to the value for path 2, and you keep doing that for every single path that exists. That is the law of total probability. Divide, conquer, then sum. But, there's a much simpler way to think about this whole thing. It's really just a weighted average. You're just averaging the chances of your event happening across all the different scenarios, but you're giving more weight to the scenarios that are more likely to happen in the first place. When you think of it that way, it feels a lot more intuitive, right? All right, enough theory. Let's get our hands dirty and make this real with a concrete example. Let's talk about 3 factories. So here's the deal. A company gets engines from 3 different factories. Factory 1 makes half of them, 50%. Factory 2 makes 30%, and Factory 3 handles the last 20%. See how that adds up to 100%? That's our partition. These are our P of A values, the size of each slice of our pie. Now, here's the twist. Each factory has a different defect rate. Factory 1 is really good, only 1% defects. Factory 3 is at 2%. But Factory 2, they're at 5%. These are our conditional probabilities. So to find the total defect rate, we have to figure out how much each factory is contributing to the problem. And when we do the math for each path, we get this. Factory 1 contributes 0.5%. Factory 3, just 0.4%. But look at Factory 2. Even though they make way fewer engines than Factory 1, their high defect rate means they contribute 1.5% to the total pile of defective engines. That's more than the other 2 combined. That is the power of a weighted average. So now we just add them up. We take our 0.005 plus 0.015 plus 0.004, and we get our grand total. The overall probability of just randomly grabbing a defective engine, no matter where it came from, is 2.4%. We divided the problem, conquered each factory, and summed it all up. Done. Okay, so we know how to use this thing, but the next big question is, when do you use it? Let's pull up a quick guide for our probability toolkit. This table makes it pretty clear. Use the multiplication rule if you need the probability of one specific sequence of events. Use the total probability rule when you have a bunch of different paths that all lead to the same outcome, and you want that total outcome's probability. And, quick preview, you use Bayes' theorem when you want to work backwards, when you know the outcome and you want to know where it most likely came from. So let's wrap up with why this rule is so critical. It's not just a neat trick for solving problems. It's actually a foundational piece of a much bigger picture. So, what do you absolutely need to remember? 1, this is your divide and conquer strategy. 2, the easiest way to think about it is as a weighted average. 3, and this is crucial, your partitions have to cover all the bases. They have to add up to 100%. And finally, you really, really need to get comfortable with this because it is the absolute foundation for one of the most important ideas in all of statistics, Bayes' theorem. And that brings us to one last, very interesting question. We know the overall defect rate is 2.4%, but what if you're actually holding a defective engine in your hands? You know it's broken. What's the probability that this specific engine came from Factory 2, the one with that terrible defect rate? Well, to answer that, you're going to need our next topic. We'll see you then.